The Big Bang theory, which has been the most successful explanation for our cosmic origins, posits that the universe began as a hot, dense, and radiation-rich state. Over the course of nearly 60 years, the universe expanded, cooled, and gravitated, forming protons, neutrons, stable atoms, stars, galaxies, planets, and complex chemistry capable of giving rise to life. However, as we continue to observe the expanding universe, the Big Bang picture breaks down, suggesting that the universe originated from nothing. This puzzle is why many scientists, including physicist Brian Cox, strongly reject the Big Bang theory. The James Webb Space Telescope has provided strong evidence demonstrating that the Big Bang wasn't the start of it all, raising questions about what existed before the Big Bang. The term Big Bang was first described over 20 years after the idea was initially proposed. Fred Hoyle, a staunch advocate of the rival idea of a steady-state cosmology, supported the perfect cosmological principle, which meant that the universe was homogeneous in both space and time. He also derided the opposing notion as irrational and claimed it was outside the bounds of science. The original meaning of the Big Bang was that the universe itself emerged from a state of non-being in the finite past. This idea evolved from the new theory of gravity put forth by Einstein in 1915, known as his general theory of relativity. Einstein's theory of general relativity shifted the concept of gravity from Newtonian gravity, which worked by causing mass to exert a force on one another instantaneously across space. With the introduction of Einstein's relativity, the notion that observers in different frames of reference would have their own unique, equally valid observations was recognized. The concept of space and time was woven together into a single fabric called spacetime, where all objects in the universe moved. A novel theory of gravity was needed to explain how not just masses, but all forms of energy, shape this fabric that underpinned the universe itself. In 1915, the laws governing gravitation in our universe were put forth, but critical information about the universe's structure had not yet been discovered. Some astronomers favored the idea that many objects in the sky were island universes located well outside the Milky Way galaxy, while most believed that the Milky Way galaxy represented the full extent of the universe. Einstein sided with this view, adding a cosmological constant to his equations to balance out the inward pull of gravity. In 1922, Alexander Friedmann worked out the equations for a universe that was isotropically the same in all directions and homogeneously filled with any type of matter, radiation, or other forms of energy. He found that such a universe would never remain static and must either expand or contract depending on its initial conditions. In 1923, Edwin Hubble determined that spiral nebulae in our skies were not contained within the Milky Way galaxy but were located many times farther away than any object that comprised our home galaxy. In 1927, Georges Lemaitre recognized that the universe today is expanding and that if things are getting farther apart and less dense today, they must have been closer together and denser in the past. He deduced that the universe must have expanded to its present state from a single point of origin, called either the cosmic egg or the primeval atom. The original notion of the Big Bang theory, which grew into the modern-day theory of the universe, was that it had a beginning or a day without yesterday. Initially, Lemaitre sent his ideas to Einstein, who dismissed them but later validated them through further observations of the universe. Many more galaxies were observed, leading to the conclusion that the universe was expanding equally and uniformly on large cosmic scales. In the 1930s, Einstein conceded his introduction of the cosmological constant as his greatest blunder. However, the next significant development in formulating the Big Bang came in the 1940s when George Gamow recognized that the universe was not only full of matter but also radiation, and that radiation evolved differently from matter in an expanding universe. Gamow made three great generic predictions about the young universe. At some point, the universe's radiation was hot enough to ionize every neutral atom. At an earlier point, it would have been too hot to form stable atomic nuclei, and at a later point, there would be a time in the universe's history after atoms formed where gravitation pulled this matter together into clumps leading to the formation of stars and galaxies for the first time. These three major points, along with the observed expansion of the universe, form what we know today as the four cornerstones of the Big Bang. A combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. The discovery of the cosmic microwave background and subsequent measurement of its temperature and black body nature of its spectrum eliminated alternate theories, such as the steady-state model. The measured abundances of light elements throughout the universe verified the predictions of Big Bang nucleosynthesis and the need for fusion in stars to provide heavy elements in our cosmos. The Big Bang is verified by our observations accurately and precisely, describing the emergence of our universe from a hot, dense, almost perfectly uniform early stage. However, the original idea of a singularity and an arbitrarily hot, dense state from which space and time could have first emerged remains a topic of debate. In the 1980s, a new idea called cosmological inflation was proposed and developed, which made predictions that contrasted with those arising from the idea of a singularity at the start of the hot Big Bang. Inflation predicted several points, including a curvature for the universe that was indistinguishable from flat to the level of between 99.99 and 99.9999%. A singularly hot universe made no prediction at all, while equal temperatures and properties were predicted for the universe even in causally disconnected regions. A non-inflationary universe produced large magnitude fluctuations that conflicted with observations, while a universe with fluctuations on scales larger than the cosmic horizon had no preference. A universe with finite maximum temperature below the Planck scale did not have these predictions. The inflationary picture has succeeded in arguing that the hot Big Bang, without inflation, must have been devoid of matter and radiation, instead containing some sort of energy. This means that inflationary expansion, unlike matter and radiation, doesn't follow a proper law that leads back to a singularity but is exponential in character. There are many reasons to believe that the inflationary state wasn't eternal to the past and that there might have been a pre-inflationary state that gave rise to inflation and possibly a beginning. There are some theorems that have been proven and loopholes discovered to those theorems, some of which have been closed and some of which remain open. This remains an active and exciting area of research still today. The original definition of the Big Bang has now changed as more evidence shows that it wasn't really the beginning of it all. NASA's time machine, the James Webb Space Telescope, found evidence of massive galaxies that defied theories of the early universe. These galaxies were so far away that they appeared only as a tiny reddish dot to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy, only 500 to 700 million years after the Big Bang. The discovery of the first star clusters in the early universe, which were expected to emerge shortly after the universe moved out of the Dark Ages, has been a subject of intense research. However, the galaxies found in the Webb images appear to be much larger and older than previously thought. This finding is in conflict with existing theories about the universe's appearance and evolution in its early years and does not align with early observations made by the Hubble Space Telescope. Previous studies of the early universe with Hubble and other instruments tend to find small blue baby galaxies at early times, objects that are building their early stars and structures. However, Webb's deep field images revealed reddish dots 50 times more massive than that. Astronomers had not expected to see old red stars or galaxies more massive than perhaps 1 billion suns. The discovery of these galaxies is also expected to overturn our understanding of star formation in the early universe. The images were obtained using Webb's near-infrared camera, NIRCam, as part of the Cosmic Evolution Early Release Science (SEWERS) program. Astronomers plan to return to Webb's mirror to obtain light spectra from these distant dots, which can reveal the chemical and physical properties of their source. Spectra will give precise distances to these objects, and knowing the distance and identity of these objects is crucial for determining their hypothesis. A spectrum will help determine if our hypothesis is correct or not. This unexpected discovery has created problems for science and calls the whole picture of early galaxy formation into question. As astronomers continue to rewrite their theories about the early universe, they must consider the potential impact on our understanding of the universe and its early stars. Expanding our understanding of the universe requires exploring beyond the initial discoveries and theories. One intriguing development is the concept of dark matter and dark energy, which are critical to our understanding of the universe's structure and fate. Dark matter is an invisible substance that does not emit, absorb, or reflect light, yet it exerts gravitational effects that can be observed through its influence on visible matter. It was first postulated to explain discrepancies between the observed mass of galaxies and their total gravitational effects. Observations of galaxy rotation curves and the movement of galaxy clusters suggest the presence of a substantial amount of dark matter that is not accounted for by visible matter alone. The existence of dark energy was proposed to explain the observed acceleration of the universe's expansion. Discovered in the late 1990s through observations of distant supernovae, dark energy is thought to make up about 68% of the universe's total energy density. It is theorized to act as a repulsive force that counteracts the effects of gravity on cosmic scales, driving the accelerated expansion of the universe. The exact nature of dark energy remains one of the most profound mysteries in modern cosmology, with several competing theories attempting to explain its properties and effects. One of the leading theories about dark matter is the weakly interacting massive particle WIMP hypothesis. WIMPs are predicted to be heavy and interact via weak nuclear force, making them extremely difficult to detect. Several experiments, such as the Large Hadron Collider, LHC, and underground detectors like the Cryogenic Dark Matter Search, CDMS, are actively searching for evidence of WIMPs. Another candidate for dark matter is the axion, a hypothetical elementary particle that is predicted to have very low mass and interact very weakly with ordinary matter. Axion detection efforts involve highly sensitive experiments designed to detect the subtle interactions predicted by axion theory. The study of cosmic microwave background, CMB, radiation has also provided valuable insights into the early universe. The CMB is the remnant radiation from the Big Bang, and its uniformity and slight temperature fluctuations offer a snapshot of the universe when it was just 380,000 years old. The Planck satellite, launched by the European Space Agency, has provided high-resolution maps of the CMB, allowing scientists to test cosmological models and refine estimates of key parameters, such as the rate of expansion and the composition of the universe. The CMB data supports the Big Bang model and provides constraints on various cosmological parameters, but it also leaves open questions about the very early universe, including the specifics of inflation and the nature of dark energy. Gravitational waves, predicted by Einstein's theory of general relativity, have opened a new observational window into the universe. These ripples in spacetime, caused by massive accelerating objects like merging black holes or neutron stars, were first directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. The study of gravitational waves provides a new way to probe the universe, offering insights into the behavior of black holes, neutron stars, and the dynamics of cosmic events. The discovery of gravitational waves has also confirmed several theoretical predictions, including the existence of black hole mergers and the collision of neutron stars. The search for extraterrestrial intelligence, SETI, is another exciting frontier. SETI involves the use of radio telescopes and other observational tools to detect signals from alien civilizations. Although no definitive signals have been found to date, the search continues with increasingly advanced technology. The Breakthrough Listen initiative, for example, is a major project aiming to scan the entire sky for potential alien signals using some of the world's most powerful radio telescopes. Discovering evidence of extraterrestrial life would have profound implications for our understanding of the universe and our place within it. Astrobiology, the study of life's potential in the universe, combines aspects of biology, chemistry, and astronomy to explore how life might arise elsewhere. Research in this field includes studying extreme environments on Earth, where life thrives under conditions previously thought to be inhospitable. These extremophiles offer insights into how life might survive on other planets and moons. Missions to Mars, such as NASA's Perseverance rover and the European Space Agency's ExoMars program, are searching for signs of past or present life on the red planet. The exploration of other planetary systems has also expanded our knowledge of the cosmos. The discovery of exoplanets, planets orbiting stars outside our solar system, has revealed a diverse array of planetary environments. The Kepler Space Telescope, which launched in 2009, discovered thousands of exoplanets and provided data that helped identify potentially habitable worlds. The James Webb Space Telescope, JWST, is expected to build on this knowledge by analyzing the atmospheres of exoplanets to search for signs of habitability and possibly even biosignatures. The study of cosmic structures, from galaxy clusters to superclusters, continues to shed light on the universe's large-scale organization. The distribution and behavior of these structures are influenced by dark matter and dark energy, providing indirect evidence of their existence. Observations from large-scale surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, offer detailed maps of the universe's structure and help refine models of its formation and evolution. In addition to observational advancements, theoretical physics continues to push the boundaries of our understanding. Quantum gravity, a field aiming to unify general relativity with quantum mechanics, remains an area of intense research. Theories like string theory and loop quantum gravity attempt to describe the fundamental nature of spacetime and resolve the contradictions between classical and quantum physics. These theories offer potential explanations for phenomena such as the behavior of black holes and the nature of the Big Bang. Overall, the quest to understand the universe is a dynamic and evolving process. As technology advances and new discoveries are made, our understanding of the cosmos continues to grow and change. Each breakthrough, whether it confirms existing theories or challenges established views, brings us closer to unraveling the mysteries of the universe and our place within it.